Welcome back to the classroom. I'm Mr. Wong. We're going to go through the problem section of the angular velocity lesson. If you haven't watched this lesson just yet on angular velocity and how to do the derivations, I do recommend you to watch that tutorial video first. This lesson or this recording is purely on solving problems related to angular velocity. So let's go. Okay, so starting from question 1, we have a wind turbine that has a blade of 55 meters in length, so that it rotates the tips of the blade traveling at a distance of 150 meters in 2 seconds. At what angular velocity does the turbine rotate? So what we need to firstly find is the angular displacement. Now think of what a wind turbine kind of looks like. Here's like my little dodgy wind turbine, and then we have the turbine down here. So it's going to rotate along the line of this. It says the blade is about 55 meters. Now assuming that the blade begins from the center of our turbine, the 55 meters also represents the radius of our turbine. It rotates a distance of 150 meters, meaning from this point all the way to this point here, we've traveled around 150 meters, okay? And this took us 2 seconds to achieve. So delta theta is equal to 150 over 55, gives us a value of 2.73 rads, or rad, for radians. The question wants us to find the angular velocity, so omega equals to delta theta divided by time. Again, we're still using the 2 seconds because that's the amount of time taken to go from one point to another. Our angular displacement is 2.73 over 2 seconds, which gives us approximately 1.37 rad per second. That's how you do this very first question here. Let's go for something a little bit more challenging. Okay, now the good old Easter show. Now Ben is on the ride at the Easter show. The carriage he is in moves in a circle of radius 3.5 meters at a speed of about 10 meters per second. What is the angular speed, omega, at which Ben moves? And then we can talk about what's the angular displacement within these 3 minutes. So we'll quote A here, omega. So that's there. So we have two formulas we could use. We could use delta theta over t, or we can use v over r. We're going to use v over r in this case because we know the radius and we know the linear velocity. Notice how I say linear velocity, not just velocity in general. So make it very clear for yourself. So it'll be 10 over 3.5, and we get approximately 2.86 rads per second. Let's go with B. So I want to find how long it takes the ride to travel, or the angular displacement, in that 3 minutes. Firstly, we need to find time in terms of its SI units. This is in 3 minutes. SI units for time is actually seconds. So 3 minutes times how many seconds in a minute? You have 60. So you get 180 seconds. Okay. Now we can use this formula over here. So it's omega equals to angular displacement over time. We already found the value of omega. It's 2.86 equals to the time travel, which is 180. And we want to find delta theta. So times this over onto this side. And we get a value of about 515 rads or radians. Okay, let's try one more. All right, Jack and Jill are playing on a merry-go-round at the playground. The merry-go-round has a radius of 1.2 meters. Jill pushes the outer circumference of the merry-go-round at 5 meters. So that's the arc length of the traveled object. At what angle of rotation? So angle of rotation, we're looking at the angular displacement. Does the merry-go-round travel through? Give your answers in degrees. So we're not using radians, we're using degrees. So keep that in mind. Okay, so angular displacement is equal to arc length. You can write it as S, you can write it as L, doesn't really matter, divided by radius. So it's 5 over 1.2. We get a number of approximately 240. Just give me a second. Went a bit far there, but the value you get here is about 1.16 repeater. Now this is in radians, so you need to times this by 180 over pi, and that will give you about 240 degrees. Okay. Next is B. What is the angular velocity? So omega. If it takes Jill 0.5 seconds to travel the 5 meters. Okay. So again, we need to actually find, or actually we already have the angular displacement. It's 240 degrees. So let's find that in both radians and also in degrees. So omega is equal to delta theta divided by the time. Okay, so if it's 240 degrees over 0.5 seconds, that gives us an answer of 480 degrees per second. If we were to do this in radians, so 4.16 repeater over 0.5, that gives us an answer of 8.3 rads per second. So there's that. Last one we have is C. Jack helps Jill push and they travel at an angular velocity of 50 degrees per second. So that's our omega. How long does it take it to, let's read that again. How long does it take to do 5 revolutions? Okay, so one revolution or one circular revolution is 360, right? 360 degrees for one revolution. So let's find the period it takes to do the one revolution. If we are traveling, so the period, if we're traveling at 360 degrees and we can travel about 50 degrees per each second, then the total time taken is about 7.2 seconds. Okay, the total time would be 7.2 times the 5 revolutions we have. So that gives us a number of approximately 38.0 seconds. That's how long it will take to do the 5 rotations based on our angular velocity. So that concludes this question here. Okay, so my last challenge for you is to try this question. The explanation is in a separate video, but this is from the 2004 HSC physics paper, worth 4 marks. It goes through the logic of centripetal force. So you have a car moving in this roundabout path here. You have a statement that says there is no net force acting on the car because the speed is constant and the friction between the tires and the road balances the centrifugal force acting on the car. Assess this statement, so make a judgment. Do you agree, disagree? Support your answer with analysis of forces acting on the car. You could draw a vector diagram, you could explain it in words using numerical data, and you need to perform a calculation at the end to sort of demonstrate. Okay, marking criteria is on this slide here if you want to have a look. So to get full marks, you need to make the correct judgment supported by arguments addressing the horizontal force backed up by numerical data. A little comment that the markers did make is better responses were succinctly identified the two clear errors. So it gives you a hint where the judgment needs to go. All right, and so that concludes our lesson for circular motion, or angular velocity technically. That's what we were discussing. We covered the problem section here. Give this video a like if you like the idea of having the theory component of the lesson and the calculation practical side split off from each other. Or if you like them both combined together, you can also write a comment down below to suggest that as well. I'm Mr. Wong, thank you for joining this lesson in physics, and I'll see you next time.